Hello and welcome to Beamer, folks. Well, this is a practical application of the circuit that I designed. One or two, probably one alteration here. The R1 750 ohms I didn't have in stock. That's, I believe, in the E24 resistive standard range. I changed it to the 820, which is my stock E12 range in this range. It alters the current very slightly, but not a great deal. The 4.7 volt Zener, just go on to that, and there it is. It's supplying 4.755 volts. Quite a good reference there, as indicated on the diagram. You go into R2, which is seriesed with R3, and I should achieve 0.96 of a volt at their junction, and into, of course, the non-inverted input of IC2, which is the TLO72A, and that's on pin 3. But here's the junction, and I'm getting bit fiddly here. I'm getting 0.98 of a volt, not quite the 0.96. There are errors within the tolerances of the resistors, but I was a little suspicious of that. I've also included across the pins 8 and 4 of IC2 a 0.1 microfarad ceramic capacitor. In the data sheet it does recommend it, and it does with certain op amps it is required to have that decoupling immediately on the power supply pins to the op amp. The excuse me, the output should be exactly identical to the input at that junction of I've got now 0.9776. It should be identical, and the output, which is across R5, is giving me 0.978. Pretty close. So it's sort of 2 millivolts difference between those two. Not a great deal of difference, but there is a slight difference, and I come to that in a minute. Across R4, which is the base of Q4 and the emitter drive of Q3, I'm getting 1.64 volts, which is going across R4. The load that I've got on this practical circuit, I've made an LED. There's no resistive dropper. It's a constant current load. It should provide the adequate current. Now if I go to milliamps on my meter, let's see what current we've got being delivered, which is, let's say, there. No, I got that in the wrong one, haven't I? Let's put that around there and that around there. Always need to pay a great deal of attention to where you plug this in. You can make a mistake and blow the internal fuse. But now I need to get the other side of my meter wire, which is the negative, and let's short out that LED to see what current we're pulling through there. I'll just confirm that I've got this right. I have. And let's just short this out. There you are, 11.2 volts. No, 11.2 milliamps. Not quite the 9.6 milliamps that I was expecting and I designed for. I wonder why that is. I think I know, and that is that R4, the 1K resistor, is with its voltage across it, is drawing a current, and it's taking that current from the connection between the two collectors and ultimately the LED load. So if I were to remove that 1K resistor R4, it should reflect more of the current flowing through R5. Let me do that. So I'm pulling out now the 1K resistor there, and let's check the current now. Let's see what happens. There we are, 9.6 milliamps. So that R4 was contributing to an error current on the output. So it looks as though that's cured. I would like a resistor from the base down to 0 volts, but I could make that a high value. It could be something like 100k or 10k, and that's it. Now let me reset back the meter back to its proper position, and let's go to volts, which is 6 volts there, full scale deflection, and hook back up my 0 volts for the meter, and one more check on the meter, make sure I've got it connected right. And let's go, let's put this 1K resistor back in for a moment, which is there and there. And what volts are we getting across it? 1.642. Right, well 1.642 divided by 1 exponent 3, that's 1000 ohms, and there you are, it comes to a contributing current in the collector of 1.642 milliamps, which accounts for that error. Now then, the difference between the input voltage on the non-inverting input of the IC2, there is an error between the input there and the output across R5 of a couple of millivolts. Excuse me. The error is caused for the fact that op amps are not ideal, and there is a difference. There's a differential pair which describes the input. That's a differential transistor pair. In this case, I think it is a CMOS pair on the input of the non-inverting and inverting, that is pins 2 and 3. To accurately to put the op amp into a more accurate position, you need to null out the input currents. This particular op amp does not have a null control, but to adjust out that difference. But I don't know whether you've noticed, but the bias current derived into injected into pin 3 of the op amp has a resistor which is R3 down to 0 volts, which is 10k. That is producing a certain bias current going into pin 3, whereas the inverting input, that is pin 2, doesn't have such a resistor to R5, which is a very low value of 100 ohms. So to help the situation, it's quite wise to put a resistor in the negative feedback, that is the unity gain loop, and that is what I'll do now. I've got here 4K7, which is an average value. If we're going to change R3 to a potentiometer, the resistance on pin 3 will vary from 0 to 10k. So what I've chosen is a resistance value which is halfway between those two, which would be 5k. My nearest, what is it, E12 value is 4K7. So what I'm going to do is disconnect the supply. Incidentally, the supply I've got via, I'm feeding this circuit via a 33 ohm resistor, 1 watt resistor. I've done that just in case I accidentally short out or miswired, and instead of receiving a large current damage, I've limited that current by this 33 ohm resistor, and when I'm satisfied with the circuit, I'll go directly to the other side of the 33 ohm resistor and give full supply value. So now I've disconnected the supply. I'll pop this onto there and put this back into the negative feedback loop, which is here. I'm having to change glasses now, so bear with me. It popped off the negative. The one thing with breadboards is you can short things out and things pop out very easily. Soldering's better for this, but when you're experimenting with stuff, it's good to be able to pull things in and out. Let's put this resistor now, which is the 4K7, in the negative feedback loop, the unity gain negative feedback loop, and see how we go. Let me put the supply back on to the limiter 33 ohm resistor and see how we go. 6 volts there. Now the reference voltage, which is the junction of R2 and R3, here is now 0.968, which is approximately closer to the design value of 0.96, and the output now is 0.969. So there's 0.96. There's about a millivolt difference there. So we have made an improvement with the 4K7, and you can see how you need to balance the input currents to an op-amp to get it to perform more precisely. Now I'll remove this 1K resistor again. I think for the moment we'll exclude it, and I'll remove it from my design. I've just thought of an additional facet of this circuit, and that is to reduce the supply and see where the output, at what point the output drops out. It should be, if you've got a 4.7 volt Zener, it's going to be, I suspect, around 5 volts, because the Zener diode will start going below its Zener point. Let me adjust it, put the output on here, which is across R5, and we've got 0.97. Now I'm going to reduce the voltage until we see that dropping rapidly. Right, we've gone down to 0.969. As I said, a Zener diode is not an ideal reference, particularly with a resistive supply dropper to the Zener diode. If we made that a constant current device feeding the Zener diode, things would be much better. But you can see already it's starting to drop, and we're at 11.5 volts. So come down, what am I on now? 9 volts, 9.5 volts. You can see it really starting to drop now. Okay, 7.5 volts. We're getting 0.95. Now I'm into 6 volts, 0.5. It's starting to fall through the floor, and that's at 6.1 volts. Well, slightly higher than the Zener reference voltage, as you'd expect. I would really want this circuit to go down to, ideally I would like it to go down to 3 volts. So I've got a little bit of work to do to achieve that. Before going on to the mirrored current source, I thought I'd wire this up for variability so that we can get precise control using a potentiometer from 0 to 1 volt. And if I adjust the potentiometer, you can see on the meter there it's reading out 1.06. The potentiometer, what I've done is I've replaced R3, which is a 10K, with a 10K potentiometer. The wiper of the potentiometer goes into pin 3 of IC2. That's a non-inverting input. So you disconnect the pin 3 from R3 connection and connect it through to the wiper, putting the potentiometer effectively looking as though it's R3. Now that's at maximum, and as I rotate down through to minimum, you will see the voltage across R5, which is the 100 ohm, linearly reducing down very nicely through to, what is that, 0.5, 0.4948 of a volt for halfway rotation of the potentiometer, all the way down through to 0 and back up again. And what I'll do now is put the meter in current mode into the in series with the LED. So I do that now. I managed to pop my 5mm pink LED, and I've replaced it with two 3mm high efficiency pink LEDs in parallel with each other. You can see now that it's the series connection with my amp meter. It's drawing 10.65 milliamps, and that is reducible linearly down to 0, all the way down, right the way down to 0, and that's good. We will discuss what do we need to do now. Oh yeah, the range. At the moment it's going from 0 to 10 milliamps approximately. That can be trimmed, and the range will be defined by R5. At the moment it's 100R, but if you were to put a 10 ohm resistor in there, you would get 0 to 100 milliamps. If you put in a 1 ohm resistor in R5, you'd get 0 to 1 amp. If you put 1K in R5, you would get 0 to 1 milliamps. So you can see that with a range selector, a selector switch, which would probably be a make before break switch, you can have an instrument that can deliver 0 to 1 milliamps right the way up to 0 to 1 amps. The BD139 I wouldn't like to see in the 0 to 1 amp range, although it's rated I think at 1.5 amps, 2 amps. The type of package that it is, the heatsink needed, required for it, you would probably be rather limited as to the compliance voltage, probably limiting it to about 10 volts DC. Bear in mind that the compliance voltage with this system can go up to probably about 32 volts. This is Beamer signing out for now.